In this video, I want to go through and talk about the second step in the regression analysis. We're going to go and take a look at estimating the betas. We've hypothesized a straight line relationship between y and x, and now we want to try to figure out how do we find the best fitting relationship to those data points. How do we know what the betas are in the model that we're hypothesizing? And so in order to do that, let's go ahead and take a look at our example. And you might remember we're trying to work with the monthly sales revenue, and we're trying to use the monthly advertising expenditure to predict the monthly sales revenue. So Y is going to be our sales revenue, and you can see the data that I collected here is in thousands of dollars. I'm making the numbers easy. I don't want the numbers to get in the way of the understanding. And so we're going to say the sales revenue is in thousands of dollars. So you see 1,000, 1,000, 2, 2, and 4. The advertising expenditures in hundreds of dollars, so 1, 2, 3, 4, 5 represents 100, 200 in increments up to 500. And so in order to try to figure this thing out, let's go ahead and take a look at the scatter plot. And once you look at the scatter plot, let's try to figure out the best fitting line. And so here in statistics, or I should say I use statistics to give me a scatter plot of the sales revenue. Okay, that's this axis over here, that's the Y. And then on the x-axis, we have advertising expenditure. And this is how the data points would shake out, how they would look on the plot. And so I want you to take a moment and see if you can figure out what's your best fitting line here. What would you say does the best job at estimating these points? And what I'm doing is I'm going to draw two lines. And the first equation is this one, y hat's equal to -1 plus x. And when I look at that equation, you can see that I've captured, or I've gone through 3 of the 5 points. I've missed 2. I don't get this guy over here, and I don't get this one over here. It misses those points, but overall that's not a bad looking line. And then my second guess, or my second attempt, is this one. Okay, y hat's equal to 2. And that's, on the surface, I think that you probably are looking at thinking, gosh, that's a terrible line. Why would you even choose that? Well, there's a method to my madness. I'll come back to that couple of videos down the road and we'll talk about that. But right now I want to ask the question, which of those two lines do you think does a better job? Now I bet everybody when you hear that question is saying, well, the red line, the y hat's equal to -1 plus x does a better job. I think that's a blue line there. I'm having trouble seeing that color. So the red line looks to be a better line than the blue line. At least that's what I think most people will say. Well, my question is, I guess there's two questions. How do we know? I mean, you're giving me the eye test. You're saying visually it looks better. But can you quantify that for me? And so we'll talk about that in a second. And then the more important question really is, okay, if we all can agree that the red line is better than the blue line, and I'm not saying that I do yet, but I'll get there. Okay, we're going to say the red line is better. The question is it the best line? And in order to answer these questions, we need some kind of guidelines. How do we define what a good looking line is, what a good fitting line is? And so that's where I'm going to go to something called the method of least squares. And we use it to find the best fitting line through the data points. And there's 2 criteria that it considers. It says, all right, let's take a look at our line and let's consider the average error is equal to 0. And this error idea, we'll say error, let's put it over here. I probably should put this in your notes. We'll say the error, how much we miss by, is equal to the true value of y that we see in our data set minus what our line predicts it to be. And you're going to see we use hats quite a bit. That's a closed parenthesis there. So when you take a look at the real value of y and subtract what we predict it to be or estimate it to be, that's the y hat, that's called the error. That's how much we miss by. And so the average error is equal to 0. Another way of saying that is the sum of the errors equals 0. So that's the first criteria. And the second criteria, I'll show you what these look like in the picture in a second. The sum of the squared error, and you can see there's our error right there, and there's our error right there. The sum of the squared error is minimized. Okay, so those are the 2 criteria. That's how the computer is going to come up with the best fitting line. That's how all the formulas that I remember from my metric algebra days, that's how they were set up to minimize the sum of squared error. And the sum of squared error, you just take the errors, you square them, you sum them up. That's where the name comes from. All right, so that probably doesn't mean a whole lot. So let's go to our picture. And I got the red pen out, so let's go to the red line. I want to point out that there's no error here. Here, these are little check marks here. Let's make the check marks a little bit bigger. Or here. What do I mean there's no error? Well, the real value of y and the predicted value of y are the same. That's why the line goes through the points. We get errors, however, here and also over here. Okay, and so I want to define that for you. Let's go a little further. So the errors are 0 at the check marks, but what about here? Well, the real value of y was 1, right? That's where the data point fell. The value of y over here is 1. The predicted value is 0, so y minus y hat, 1 minus 0. So the error associated with the red line and this data value is positive 1. How about over here? The real value of y is 2, and my line predicted it to be 3. So 2 minus 3, negative 1. And for each of these check marks, you have 0. So sum up all those errors, a negative 1, a positive 1, and a couple zeros, 3 zeros. So the sum of the errors is equal to 0. And the average error, if the sum is equal to 0, the average error is equal to 0. Okay, so that works. That's the first criteria. Okay, now sum those things up and you get 0. Let's say sum of the squared error. That's what I was trying to say there, and it didn't come out right. Think about it. Square those values. Square the positive 1, square the 0, square the 0, square the negative 1, square the 0. The sum of squared error here is 2. Okay? Just math. Just playing some math games with you here. The average error is 0. The sum of squared error is 2. Now let me shift pens and let's go to the blue line. So the blue line misses here. It misses here. It gets here. That's a 0. Oh, look at that. It hit that one too. And then it misses pretty badly here. Okay, so let's take the y. The y value is 1 minus the y hat. The y hat here is saying 2. This is an interesting line. If you think about this line's saying we're going to guess that the value of y is 2 regardless of what the value of x is. This is a line that actually ignores the x's. It's an interesting line. Again, we'll come back and talk about it again later, but we'll just use it as a comparison here. And so the error here is negative 1 because the real value is 1, the predicted value is 2. The error here is excuse me, negative 1. The error here is 0, the error here is 0, and the error here, let's see, the real value of y is 4, and the predicted value is 2, and so the error here is positive 2. So again, when you sum all the errors, negative 1, 0, 0, positive 2, the average error, the sum of the errors is 0, but let's look at the SSE, the sum of squared errors. So take those error values, really think about what we're doing here, how much we missed by. Take our misses, square them, and sum them up. Well, for the blue line, we have a negative 1 squared, that's 1, there's another 1, and there's 4. The sum of squared error is 6. So as I look at these two lines, here's what I'll say. The average error is 0 for both of them. In fact, any line that you draw through this point right here, this is kind of the pivot point. Okay, if I draw a line, see if I can do this with my mouse. Oh, that's a terrible looking line. You're just going to pretend that that's a good looking line right there. That line is a terrible fit, right? That doesn't fit the data all that well at all. This green line I just drew, but here's what I know. The average error of that line is 0. Anytime it goes through this point, you're going to get an average error of 0. And so really what we're thinking about is let's rotate this line and try to find the one that has the best fit to the data. And all we've shown is we've looked at two of them. We looked at the red line and said the sum of squared error there is 2. We looked at the blue line. We said the sum of squared error there is 6. The conclusion we should get is that the red line is better than the blue line. And you're probably thinking, way to go, Mark. I knew that 5 minutes ago. I get it. I understand. But I wanted to try to explain it a little bit to you. All right. So if the red line is better than blue line, is it the best line? What's the best fitting line? And in order to do that, I'm going to go to the software, the Statistix software, and I'm going to ask it to generate a printout. Now, I'll show you how to generate these printouts in other videos, but this is the result. These are the regression results you get. And this printout has a lot of information on it. I'm trying to see if I can do a highlighter. Yeah, let's a thick pen. Let's see what happens when I do this. Let's see if it writes through the points. Yep, we don't want to do that. All right, so it was worth a shot. Let's go and erase that. I'm going to get the other pen back. Up here is where our coefficients are going to show up. That's what we're looking at now. This is our estimate of the y-intercept right there. This is our estimate of the slope parameter right there. And so from this equation, or from this printout, we're going to get the equation of the best fitting line. We're going to say y hat is equal to negative 0.1. The constant refers to my estimate of the y-intercept, plus 0.7 times x. And we get that from this part of the printout. We see that in simple linear regression. As we go further in multiple regression, that's where that information is going to be. As we go in multiple regression, the number of variables that get listed here increases. We may not just have advertising expenditure. We might have the number of salespeople. We might have advertising expenditure squared. We might have some interaction components. We might have a whole bunch of stuff. And so this part of the printout, this upper part here, the number of rows expands. Okay, that's where that information is. You can see that these numbers here are bolded. That number is bolded. That number is bolded. There's going to be another part to the printout later on. All of those things factor into the 5 steps that we're working our way through in simple linear regression. Right now, the only piece we need when we're estimating the betas is this piece right here. That's where we're at in this printout. And so I'll move forward now, and I'll say, before I show you the interpretations, that's the line. I asked Statistix to actually go ahead and put the line in. Remember the one that we were looking at, the red line went through this point, and this point, and this point. If I can go back, I don't think it's going to let me go back. Shoot. Look back in that printout. In the bottom part of the printout, you will see it says source degrees of freedom, SS, MS, F, and P. There's the very bottom of the printout. There's a regression, and then there's a residual. If you look on that residual row, and you go across to where it says SS, of the residual, you see 1.1. That's the sum of squared error. The sum of squared error of this line is 1.1. Here's an offer I'll make to you. This is the best fitting line. This is the least squares prediction equation. What's that equation again? Y hat is equal to negative 0.1 plus 0.7 times x. Here's an offer I'll make to you. If you can find a line that fits this data better than this one, that has an average error of 0 and has a smaller SSE, I'm going to give you an A for the semester. In fact, I'll give you a 4.0 for your college career. How can I make such an offer? Because it can't happen. You can't do it. The best fitting line is the best fitting line. That's the one we get on the printout. And so we're going to let the printout give us the line. I'm going to ask you to tell me what the numbers represent. That's what I'll do on the next page. The beta interpretations. We have a y hat equal negative 0.1 plus 0.7x. What's the 0.1? Well, the 0.1 is our estimate of the y-intercept. When advertising, how do you interpret a y-intercept? The y-intercept says when x is equal to 0, this is what we estimate y to be. So when advertising expenditure is $0, we estimate sales revenue to be negative 100. Why is it negative 100? Because remember, sales revenue was in thousands of dollars. What's negative 0.1 in thousands of dollars? Negative $100. A lot of times when you're interpreting y-intercepts, you might be looking and thinking, what? That's crazy. Negative $100, is that possible? Sales revenues can be negative. What if you have a whole bunch of returns? It can be negative, but a good question to ask, something I always want you to ask when you're working with y-intercepts, is this practical? Does that make sense? And not in terms of, hey, I don't like the number negative 100, but here are 2 questions that you always have to ask yourself when you're working with the y-intercept. First, does the value of x equals 0 make sense? And put that in the context of this particular problem. Can you have a month where x is equal to 0? Can you have a month where advertising expenditure is $0? Is it possible to not spend anything on advertising? And the answer, of course, is yeah. It is possible. Sometimes the answer is no. Remember how I told you, I think I mentioned, regression got its start trying to predict heights of children. A bunch of guys were standing around, statisticians, that would have been a fun group to be in, but a bunch of guys are standing around saying, hey, I think my boy's going to be taller than your boy. And they decided to work together to come up with a mathematical relationship, try to predict the height of their son based on their height. So son's height was the dependent variable. Dad's height was the independent variable. Now, I'm sitting here. I'm about 5'10", 5'11", somewhere in there. Let's say I'm 5'10". That's 70 inches tall. And so we would use my height and a bunch of other guys' heights and try to use a mathematical relationship to predict the height of our male children. That's how it got its start. It's terrible. I wish I could tell you we were trying to save the world. Nope. We were trying to predict our boys' heights. Bunch of dudes standing around. Bunch of math geeks standing around. Anyway, moving on. Does it make sense for x equals 0 in that particular example? Well, x, the independent variable, is dad's height. Does it make sense for dad's height to equal 0? Can you have a dad who's 0? And of course the answer is no. That doesn't make any sense at all. And if that's the case, we would say that the y-intercept, the beta naught hat, is not a practical interpretation, since the value of x equals 0 doesn't make sense. And you might be thinking, well, that's kind of a strange example. Think of your data sets. You're trying to predict the price of a house based on the size, the price of an apartment based on the size. Does it make sense to have an apartment or a home with 0 square feet? Is that even possible? Can you predict the price of a car on the mileage? Can you have mileage of 0? And again, theoretically, you might say, oh yeah, you can have mileage of 0. Can you? Really? Even new cars have a little bit of mileage on it. But you guys are sampling used cars, right? Can you have a used car with 0 miles? And the answer should be no. But there's a second question. We can argue theoretically, well, you could have. Did you sample over the range that included the value of x equals 0? Later on in this regression topic, we're going to talk about a topic called extrapolation, and that's where we use our model outside where we should. We stretch it a little bit. And really what we're going to say is, what value of x's did you include? Look at the mileages on your vehicles. What's the smallest? What's the largest? That's where you live. That's where this model will work. Take a look at your apartments, your homes. What's the smallest? What's the largest? That's the square footage that this works for. If I'm trying to predict the height of male offspring, take a look at the smallest dad, the tallest dad. Yeah, it works there. Don't go above the tallest dad. Don't go below the shortest dad. The value of x equals 0 is not included in that range. If all your homes are between, say, 1,500 and 3,500 square feet, don't try to predict a 4,000 square foot home. It's outside the range of the data you sampled. Likewise, don't interpret something when x is equal to 0, and that's the y-intercept. A lot of times, the y-intercept interpretation is iffy. It's not practical. So you got to be careful with that one. The slope interpretation, that's not iffy. And so let's take a look at that. That was the 0.7 value. What's the slope of a line? Well, back in the day, I remember talking about slope as rise over run. What does that mean? Okay, think about it. We have a little, let's see if I can draw a decent little picture here. It's supposed to be a straight line. That's a little bit better. Rise over run. As you run this way, the rise is what we call the slope. It may be a negative slope. If you're working with the automobiles, as the mileage increases, you actually expect that line to go down, right? And so what we'll say is for every 1 unit increase in x, that's the run, this is what we expect to happen to y. For every 1 unit increase, well, we're talking about $100 here. For every 1 inch increase in dad's height, that's how I would do it in that other example. For every 1 unit increase, $100 increase in advertising expenditure, we expect sales revenue y increase, because this is a positive number, by $700. If you're working with the automobiles, you're expecting a negative value there, aren't you? You're expecting for every mile increase, the price to decrease. In apartments and in homes, you're expecting for every 1 square foot increase, you're expecting the price or the rent to go up as well. And so what we're looking for, what we're expecting, depends upon the type of data that we're working with. And so that's how we interpret the betas. Now, big statement here. The beta interpretations, we have a slope and a y-intercept. The beta interpretations are very specific to the model that you're working with. We're working with a straight line. The simple linear model has a slope and it has a y-intercept interpretation. What happens if we start talking about curves? We don't have slopes. A curve doesn't have a slope. It's an ever-changing slope line. Does that even make sense? Probably not. It's a curve. And so we're going to have different beta interpretations for different models. And so the beta interpretations can get a little tricky. Fortunately for us, the beta interpretations, while they make sense and they're easy to work with here when we're working with simple linear regression, that's not the emphasis. That's not the focus. We don't really care so much about the beta interpretations. Yeah, we might get some useful information, But what do we care about? We want to predict Y. This is all part of that process. We're trying to figure out, can we predict Y? Can we predict the sales revenue? Can we do that? Is it effective? Is it useful? And we'll talk about some of those ideas. So step one, we hypothesize a model. Step two, we estimate the betas, and really for you, it's more about interpreting the betas. The method of least squares is what we use. We get numbers on a printout, and I'm going to have you guys do the interpretations for me. And so that's the second step. The next step is to go ahead and get ready for the testing and the confidence intervals. But before we can do that, we need to mention some assumptions for the epsilon, and we need to estimate the standard deviation. And in order to do that, I'll come back and do a different video. So long.